My name is Vladimir Peskov. I will present, on behalf of our team, the latest progress in our project, Attract Smart. First, our third SMART paper focused on systematic studies of high sensitivity detectors of dangerous gases is in progress. Second, with the support from RD51 Common Funds, an innovative spark-protected micropattern detector was designed and manufactured. It made of microwires supported by small pillars produced by microelectronic technology, as in micromegas. Its main advantages are much lower operation voltage and imaging capability. It represents a new generation of avalanche detectors for smart integrated system. The tests are in preparation. Third, based on results obtained during Attract Phase 1, the concept of the commercial smart system was developed, see next page, and in collaboration with the Italian company Naycam. The schematic of future Attract commercial prototype system is shown on the next slide. It will be a fully automatic system containing several detectors operating in parallel and communicate with each other and with a common computer center. In particular, it will consist of a sensor of flames and smoke, sensor of dangerous gases, flammable, toxic, radioactive, and a detector allowing to visualize flame and smoke and to determine their position. Their operation principles were described in earlier presentation and in 2 our SMART papers. So I will skip this subject and will only mention that they are based on CERN technology, which is not spread yet to industry. Due to this, our smart sensors will have superior characteristics compared to commercial one. Several new features will be implemented in the commercial smart device. For example, pulsed UV lamps, signal from which, in case of appearance of dangerous gases or smoke, will automatically switch on depending on a concrete situation, either a system for dangerous gases analyzing or an electrical cleaning system based on corona discharge. These measures will allow smart operating in harsh environmental conditions, which will be another advantage of our system compared to commercial device. Of course, we are also planning to implement in this smart commercial device this micro wire detector, which I showed you on the previous slide.
Here is an update on the MULTIMAL project, the point-of-care device for non-invasive multiplex diagnosis of malaria. Since October 20, the sensor chips were tested in different human conditions, in particular those defined by regulatory agencies and that correspond to the worst-case storage conditions in tropical countries. The performance of the sensors was positively assessed. In the last days of the funded project, the sensors were tested using a culture of malaria parasite to verify the detection levels down to one single parasite. The obtention of biological samples from real patients is still under negotiation with the local hospital, also pending the return of international flights for more patients returning from a risk area to ask for a test. The members of the team have been following an entrepreneurship mentorship program organized with a third-party partner, including working to define a brand and an image, exploring product design, and preparing to pitch investors. A patent on key aspects of the technology is expected to be submitted until February 2021, and to date, the patentability search was done. And finally, a proposal was submitted to a private foundation to try advance some research and technology aspects that would come as a complement to possible funding from the Attract consortium.
Hello everybody, this is Juan Manuel Madariaga. the coordinator of the CORaHE project. When we finished phase 1, we reached TL4 in the development of our cold Raman head sensor. Since then, we have made some progress. We have started the designing of the new prototype to reach TL7 at the end of phase 2. We have selected a new lubricant to guarantee the performance of the microscopic stage when working at -30 degrees, maintaining its lateral resolution of ±1 micron. We have increased the number of chemicals, inorganic and organic, of our Raman database. And moreover, we have included the Raman profiles of the same compounds at different low temperatures. To go with the industrial product, we have defined several steps. As mentioned, we have started working in the new design for the head and the spectrometer to reduce the size and the weight of the final product, increasing its portability. We have started with the designing of a calibration holder that will be developed for each particular use of the device. We wish to include Raman imaging capabilities to see the distribution of the chemicals, like it is observed in the images in the left. And based on those modal distribution of the chemicals, we wish to include quantitative analysis. And finally, we will develop a more familiar user interface for an easily handle of the whole device. Initially, our consortia was formed by 3 partners: one company, one technological centrum, one university. Now we are going to expand the consortia, including 2 new industrial partners. One company in the field of instrumentation with expertise in Raman spectroscopy to couple deep ultraviolet Raman spectrometer with the new CORaHE head, making it portable. And the other company with distribution capabilities and with expertise in manufacturing Raman accessories for field analysis, because we know that each particular application in the field, in a company, whatever, requires some special accessories. Which kind of applications are going to be demonstrated in this phase 2? We have selected some for security and health of human consumption of foods, for studies in climate change, for labels of quality control in companies, for rehabilitation and preservation in cultural heritage. Once the prototype is protected, we plan to present our instrument in its functional form to potential investors. And in the case the market is not receptive to our product at the stage of TL7, we plan to obtain public or private funding to develop further the product, reaching TL9 to put it in the market.
Good morning. I'm Professor Sergio Saponara from University of Pisa, and I'm speaking on behalf of the iPhoSpace consortium in order to show the last achievement since October 2020 in view of the ACTRAC Phase 2 kickoff, where the iPhoSpace consortium aims at a scale-up at higher TRL. The goal of iPhoSpace is the radiation-tolerant, high-speed optical data links development, targeting not only high-energy physics domain, but also application like space. The last achievement since October 2020 are related to the fact that came back drivers developed in 65 nanometer technology, and so we were able to completely characterize them in terms of electrical, functional, thermal characteristics, and so it was demonstrated a bandwidth increase from 5 to 9 gigabit per second per channel for each optical modulator driver versus the previous generation developed in iPhoSpace. And moreover, this driver were also characterized with the X-ray radiation testing at CERN, and the results confirmed correct operation up to 1 gigarad total ionization dose. It has 10 megagray. So also here increasing the performance of the previous generation. Moreover, in the last month of 2020, there were also the finalization and the submission to the foundry of the tape out of a 28 nanometer ASIC, integrating an optical modulator driver plus a voltage controlled oscillator for phase lock and loop and clock data recovery. In such case, in 28 nanometer post-layout simulation proved that it's possible to achieve 25 gigabit per second per channel, and we hope this will be confirmed by experimental testing. And also there was the submission in high-mech silicon photonics technology of a complex silicon photonics chip integrating different optical modulators type with different also characteristics. So several Mach-Zehnder modulators, several ring resonator, and several electro absorption modulator that will achieve to increase the characterization and so the TRL. Beside this technical achievement, also in the last month of 2020, there were the new potential application and synergy for iPhoSpace in Attract 2. First of all, beside the already mentioned high energy physics and space, also there can be an interest for the Euro HPC community, since the goal of a high TRL for 100 gigabit per second integrated photonic link in iPhoSpace is a key enabling technology also for the interconnection of chiplets that is foreseen in the roadmap of the European Processor Initiative, and this can be at the basis of the future European exascale machine. So a new market, the Euro HPC market, can be a target of iPhoSpace. And moreover, recently started some project like Falafel for ENFN, and R&D on experimental technology at CERN, and again University of Pisa and ENFN involved in the Euro HPC project at Testarossa, with which iPhoSpace can find synergy, and this will help to reach a high TRL and a good scale up in Atlas phase 2. Last but not least, there was also a further update of the expression of interest, since already beside the phase 1 partner like CERN, ENFN, University of Bristol and KIT, there were added interest from University of Pisa, and particularly from two companies, a small medium enterprises engineers and Thales Alenia Space, a big company, both working in the aerospace domain. But there was still, end of 2020, a further interest from Bryonics, an Irish small medium enterprises which is active in the photonics integration and packaging technology, and particularly also with potential application in the space and HPC domain. And so this new consortium, so that in phase 2 is enriched with several companies, can ensure that iPhoSpace can be successful in Attract 2, scaling up and reaching the desired TRL, serving, as I said, multiple markets. So not only high energy physics, but also space and Euro HPC community.
In the hospital, pathologists are exploring tissues to look if there are signs of cancer. To do so, they remove small bits of tissues called biopsies that are embedded in wax, slice, stain, and finally observed by trained pathologists. This labor-intensive process is known as histology preparation. It takes 24 to 72 hours. A faster and degraded process, known as extempo histology, uses cryosections and staining and takes 40 minutes. The dream would be to have an imaging platform that allows instantaneous histology directly in the operatory room to immediately identify cancer tissue and to remove them. This would save life, this would be beneficial to the patients, and this would save money. In the Attract phase 1, we have conducted the SRHisto project, where we have developed a novel imaging technique that can perform label-free histology of freshly excised human tissues in a timescale that is 10 times shorter than the standard histology of frozen section. We use for that the stimulated Raman contrast, that enables label-free imaging of chemical bonds present in tissues. We have developed a stimulated Raman histology protocol that enables virtual histology section in less than 5 minutes. We have developed a low-noise laser source demonstrator that enables to acquire simultaneously stimulated Raman images for the cell body and the cell nuclei. These images are further processed in a software to change the stimulated Raman images in histology-like images that can be readily interpreted by medical doctors. We finally have validated the technology with hospital practitioners on gastric and brain human healthy and cancer tissue sample. On the left, you can see a stimulated Raman histology image as compared to the standard hematoxylin and eosin H&E histology image, and on the bottom left, the overlay of the two. In the ATTRACT phase 2, we want to move from the lab demo that we have built in ATTRACT phase 1 to a fully integrated imaging platform that enables instantaneous histology. This would move the project from TRL 5.6 to TRL 7.8 in 18 months. In ATTRACT phase 2, we want to provide instantaneous histology thanks to our imaging platform, and to be able to directly work on freshly excised biopsy samples without any preparation, to provide instantaneous virtual histology that can be readily interpreted by trained pathologists, and at the same time to provide a machine learning diagnostic that will identify into the tissue the cancer and the healthy parts. The consortium that we want to build includes a German company, APE, specialized in light sources, a French company, Lightcore Technologies, that will build the stimulated Raman microscope, and an academic institution that will be working on the virtual coloring and the machine learning. This consortium will interact with hospital in the gastric and the central nervous system in order to demonstrate that stimulated Raman images are valuable in the operatory workflow. The roadmap for this ATTRACT phase 2 project will be to build a stimulated Raman imaging platform suitable to be used in the hospital, to conduct a non-inferiority studies as compared to standard cryosection histology, and to demonstrate the relevance of the technology in the operatory room for cancer diagnostic. This will also lead to the agreement for hospital use. While this validation will be in process in the hospital, our goal is to sell the platform, the stimulated Raman microscope, after 18 months to researchers in biology, medical science, pharma, cosmetic company that are routinely doing histology to address their research problems.
Hello, I'm Pierpaolo Valerio from University of Geneva, and this is the update for the ATTRACT Phase 2 kickoff meeting on the MonPicoAD project, a monolithic picosecond avalanche detector. The MonPicoAD project aims at developing a novel monolithic pixel detector that can achieve a time resolution of a few picoseconds. It's based on 3 different parts that will be developed independently. One is a fully depleted multi-junction sensor with a buried gain layer, and the other 2 are the electronics. So a fast front end based on silicon germanium BJT devices, and a picosecond level TDC. A prototype chip that includes all these parts has already been fabricated and is currently being tested. You can see the cross-section of our sensor in the slide, with the N wells forming the pixels lying in a p-doped substrate. And the novel idea of the sensor is the presence of those 2 buried doped layers, an N region and a P region, and those create a gain layer in a very shallow region of the sensor, providing great timing resolution for our signals. After a lot of work with the help of the foundry in order to produce this sensor, we finally have our hands on a prototype. So we started measuring IV curves in order to assess the validity of our idea. We can happily say that this idea works according to our simulation. So the measurements match our simulations pretty well. You can see that by increasing the high voltage, the sensor gets depleted, and you can see the two kinks, which is the first one is the moment in which the depletion reaches the buried layers, so the charge trapped in those layers get flushed out, so there's a peak in the current. And the second one is where the depletion region reaches the guard ring of the structure, so some current gets diverted to the guard ring. But after that, there's the gain region, and this is exactly how our TCAD simulations predicted. We also were able to irradiate our sensor with an IM55 source in order to assess the gain layer. And we can see that the IM55 source produced two different peaks in our sensor. One if the charge is collected in the top part, and one is if the charge is collected on the bottom part below the gain layers. And we can see in the plots that by increasing the high voltage applied to the sensor, the second peak moves to the right, so it separates from the first one, indicating that the second peak actually has a gain, so the charge collected below the gain layer gets multiplied by going through it. We're also testing the front-end electronics on a test chip with the standard substrate, so without the gain layer, in order to decouple the measurements of the two blocks as much as possible. And we tested the chip at various configurations, various working points at different power consumptions. And the power consumption is always pretty limited, so even our highest power consumption point is at 150 milliamps for the front end. And we can go down to 35 picosecond time resolution, but even by reducing the power consumption considerably, so going to less than 10 microamps, we still are at about 100 picosecond time resolution, which is very interesting for a variety of applications in which the power budget is a more important figure of merit. Of course, more tests will be needed on the sensor in order to assess how much the gain is and how stable it is at different biasing voltages, also in order to optimize the fabrication procedure in order to make it easier for the foundry to fabricate it. Tests on the electronics is still ongoing, and especially the TDC design needs to be validated. We have received the samples back from the foundry, but we still have to test it. There's also a more complete TDC design in a fully standalone chip that has submitted in January and will be ready to be tested in about 6 months. Lastly, we will test the full chain, so a prototype chip on the gain sensor once every block will be validated.
Welcome to the presentation by the Instant Collaboration. The acronym stands for Imaging in Space-Time and Tracking, and the project aims at the fabrication of an integrated and compact device capable of extraordinary precision in space and time measurements to sustain very high processing rates and to operate in harsh radiation environments. The very core of such device is a 3D silicon sensor exploiting a trench geometry of the electrodes, having 55 micron pitch and no internal gain. The most relevant result in these last months of activity was the break of the 1 picosecond barrier in time resolution demonstrated with our sensors. This was obtained using an infrared laser pulse, which mimics the deposit profile of a particle with a 10 MeV equivalent energy. In these particular conditions, time resolution improves from the 6.5 picoseconds obtained with a 1 MIP equivalent to about 900 femtoseconds. We have also elaborated a method to obtain the same effect in ordinary conditions by adding a small gain stage on top of the device. Other very important achievements have been accomplished on the sensor modelization by developing a custom simulation code and systematically validating the model output by experimental tests. We have now a complete control of the internal sensor behavior and have a deep understanding of the experimental time distributions gathered at TestBeam 1 year ago. Last but not least, we completed the design of a custom prototype ASIC capable to read out about 1000 pixels and equipped with a high-performance TDC per channel. Post-layout simulation results are very promising, with resolution of around 15 picoseconds on the full readout chain. Giving now a glance to the future, we understand that we have in our hands all the main ingredients to construct an instant device, but we still need a relevant work to perform integration studies and develop a really compact and production-grade device. For these reasons, we would like to establish a working collaboration with advanced integration and packaging developers. Important application of the instant device can be envisaged in advanced photonics and biomedical equipment. Therefore, collaboration with end-user developers in these fields would be very fruitful during the device development phase. The instant device has clear applications in fundamental high-energy physics, especially in the next generation of high luminosity, high-energy experiments, which will have important pile-up issues in tracking operations. Other relevant applications are in biomedicine, as for example in hadron therapy or in vivo radiology, and in high-performance photonics, whenever extreme concurrent space and time resolutions in radiation detection are important. In looking for investors to help making our development a real integrated system, we would naturally start from our high-energy physics industrial network and application-specific funding agencies, but we also count on the Attract Consortium potentiality to bring together the two communities of researchers and investors. We will continue to actively participate into any possible initiative promoted in this direction. At any rate, we will surely explore any source of funding in the future, being strongly convinced of the great potentiality of our development. Thank you for your attention.